Now we will go through the GAN architecture, and then we will try to explain that how easily we can write the code for GAN architecture, and we can easily do a lot of experiments with it. So let us go through it. But one thing that I will clear, that instead of using the traditional vanilla GAN, I have used the deep convolutional GAN. So DCGAN architecture. The main reason is the traditional GAN architecture is actually suffering from problems like mode collapse and some training stability and then overfitting, etc. That's why we have decided to select the deep convolutional GAN architecture. In the deep convolutional GAN architecture, the system uses convolution and deconvolution concept. So in the generator model, it uses some deconvolution concept, and in the discriminator model, it uses the convolution architecture, deep convolution architecture. Due to this, it little bit lowers the effect of mode collapse and training stability and overfitting. So this is the reason I decided to cover this deep convolutional GAN architecture, and this is useful also in a lot of different applications. So first of all, start with the data set. So here we can see that we have used a noise of 100 size array to train the system, to train the generator model, and then generator model generates an image GZ. Now one question you may ask, like, why we used the vector sampled from a normal distributions and why mean equal to 0 and variance equal to 1. So when we are selecting the random noise, then what is the use of those things? So the answer is, when we use the normal distributions or Gaussian distributions kind of things, we get some computational efficiency in handling all the data. We can easily handle those data. Again, a lot of samples generated by such kind of concepts generally comes under central limit theorem, CLT, and we can say that it is robustness to scale also. So robustness means when we take the normal distribution samples and multiply its mean and standard deviations through some scalar, then even through the generator models operations, it doesn't leave its original characteristics. So we can maintain some characteristics. Again, you can say that y mean equal to 0 and variance equal to 1. So this is very easy because we are trying to maintain some simplicity by controlling the data by using mean equal to 0 and variance equal to 1. Now the other questions will be like that, other than normal distributions, can we use any other different type of distributions? Yes, we can use. We can either use uniform distributions, we can either use Laplacian, we can either use logistic type of inputs. So it is based on the requirement. So this is the like a noise data. Now here in the current case, we have used, to explain the entire example, we have used the MNIST data. So here you can see that this is MNIST data. So the entire MNIST data actually contains the 28 into 28 pixels images, and all images are handwritten 0 to 9 digits. So it contains total 60,000 training and 10,000 testing images. So once we generate the noise, we go through the generator model. Now let us try to understand that how generator model is actually working. So generator model takes the data and then it uses some deep neural network or some general perceptron architecture type of architecture to just we can see that is a project the 100 size array input to a 3D array of 128 into 7 into 7, and then we reshape it like a 7 into 7 into 128. Now the main part started, for which we have taken for which due to which we have taken the deep convolutional GAN architecture. So this is called conv 2D transpose, like this is called transposed convolution. So this is called transposed convolutions. The main purpose of this transposed convolution is to increase the size of images. For example, from input 100, it can increase it to like 28 into 28 into 1. So what is the use? This we call this like a deconvolution or expansion of images. So what is the role of those kind of expansions? So the main role of those expansions are like main benefit of those expansions are by this kind of expansions we can get high quality images. So but before that I think we should go through like how it is possible. So how the transposed convolution is actually working. So the transposed convolution actually converts the data from lower dimension to higher dimension. We can say it like nearest neighbor interpolation kind of thing. How it is doing? Suppose we have a data, simple data A, B, C, D. A simple data is there, and now we have a kernel, transposed convolutional kernel is like this. So we have this 4. Now we have to enhance this data. So in that case we generally use some padding. We suppose we are using some kernel size padding, and to meet that kernel size and our requirement, we can do some padding like we can add 0 0. So we can add this, and after that by taking this kernel and applying the kernel movement like this, and then this, and then this, we can easily get a 3 by 3 output images. So this way, so one important thing you can see this why it is called the nearest neighbor convolution, because here the padding, so near to the padding it uses some the nearest neighbor data, and again it try to use the this range, and then it uses this range. So the projection of those ranges actually helps us in enhancing the quality of the network, the quality of the images. So here you can see through one example also. So I have just written a simple example like how it actually works. So here you can see that we have some input matrix and kernel, 2 by 2 kernel, and our target is to transpose convolutions, achieve the transpose convolutions of 3 by 3. So same way through the convolutions it will generate the result. So here you can see that for this data and this input matrix and this kernel, it has generated this kind of output. So how to generate and how to do the convolutions operations, for that I have already prepared the video, so you can go through the my other videos, previous videos. So okay, so this is the way to do the means upsampling. So this is not just a single this is not just one way to do the upsampling. There are multiple ways to do the upsampling. Some other ways, in some research paper they say that instead of same padding, because we are using the, suppose in several ways we are using same word same as a constants in the coding when we do the upsampling. So in that case only we do the expansion, like that we use additional rows and columns for the data and then do the padding. But in other case we can do the padding in between the data also, and we can also do the padding if the same is not there. So there are multiple different ways to achieve the upsampling. So I have just discussed the one. So after this upsampling we are able to enhance the size of the data. So now you will be able to understand that how upsampling is different from, means this is called deconvolution, is different from convolution operation. So in the convolution generally what we do, we take suppose 3 by 3 matrix and reduce it to 2 by 2 matrix. So it is generally downsampling. So all the convolutions operations are actually downsampling. Several times we say it like upsampling, like a stride based upsampling or stride upsampling also. Why we say it like a stride upsampling? Because when we traverse in a matrix and suppose our stride size is equal to 1, then it is easy, then we can directly move. So the level of enhancement in that matrix we get is very easy to get, means it is directly, because it is s equal to 1, stride equal to 1. But if we stride equal to 2, then we have to just leave the 2 points and then we can move the next 2 point, then we can move to the next point. Same we can do the up direction towards the left direction, right direction, and same towards the bottom directions. So this is the way, and it affects the size of image that we generally generate through the upsampling. Now the next part is batch normalizations. So for batch normalizations, actually it is very easy. Batch normalization actually reduces the impact of internal covariate shifts and which may result the overfitting in the output result. So that's why after each of the deconvolution operations, a batch normalization layer is applied. So here you can see that after batch normalization again another conv2D transpose layer is applied, which do the deconvolution operations, and it converts the image of size 14 into 14 into 128 to 28 into 28 into 128. Now again a batch normalization layer is applied. I have prepared another tutorial on batch normalizations, like how it is working, how it is affecting the internal covariate shift, why it is useful and how it is useful, everything. So now after that we pass the output to the convolutional architecture, 2D architecture. It generates the image of size 2D into 28 into 28 into 1. So this is same like we have shown in the MNIST dataset, that size of the image is 28 into 28. So channel equal to 1 means for 1. Now the next part is, so now we are able to understand that what is generator model and how it is working. The next part is discriminator model. So what is discriminator model and how it is working? Discriminator model is nothing, it is just like a classifier. So in the deep convolutional GAN architecture, you can see that it takes the input of 28 into 28 into 1 type of image, apply some convolutional operation, and then apply some dropout. The main purpose of dropout is to just reduce the overfitting the effect of overfitting, and it gradually reduces the size of images, and then finally a dense layer or sigmoid layer is applied to calculate the probability or classify whether the image is real or fake. So this is very simple to understand.